Okay, can I start or can you hear me?
Yes, we can hear you.
Okay. Um, so yeah, thank you very much for the invitation. Maybe Franco is not here, but he invited me, and of course, I thank all the organizers. And I discussed my topics is superconducting qubit and even computer. And I have been doing this for a long time. So, and I discussed with Franco that what kind of talk, the new development or something fundamental or physics. Franco and I agreed, maybe since this is his first talk about superconducting qubit, I will talk a little bit more about fundamental physics. And then I'll talk about a little bit about the quantum computers based on qubit, superconducting qubit, and I show you my recent, a little bit of my recent research in RIKEN and Tokyo University of Science. I have two affiliations, and okay, the first time I heard about quantum computer, it's excuse me, I cannot see this. It's 84. Okay, 1984 when I just graduated a PhD in Stony Brook and went to NEC in Tokyo, and Feynman came to Tokyo, gave a talk in Gakushuin University, and his title was Computer of the Future. And I was so excited. I was working on a superconducting computer, Josephson computer at that time. So I was very curious about Feynman talking about computers. And then his talk, everyone was so surprised. And he said, in the future, the transistor will get smaller and smaller, and finally, it became, it's atom, 3 atoms. You can make a switch. You change the states of the central atom. Let me get the pointer. Then you can connect to atoms by a switch. It's like a transistor, and at that time it was so too fantastic. Nobody can believe it. And also he talked about quantum coherence. With this system you can control quantum coherence, and he talks about quantum simulation, kind of, making wind tunnel using quantum technology. And he didn't really talk about digital computing, but something like quantum simulation, I think. And but I guess no one really took this seriously at that time, including me. And we all thought, Feynman went crazy. This is, it's a great physicist, but he's crazy. But then I forgot all about this. But 23 years later, we did this work. This is the superconducting qubit, a two qubit gate, quantum gate in 2007. And this is 2 flux qubit coupled by another flux qubit, and it works like as a switch. It makes a beautiful gate. And then I realized Feynman would just talk about this 23 years ago. And I was really, really surprised that, the development in science is so unpredictable, and it takes some genius like Feynman to lead us the way. It was a good story. Anyway, so my subject, I was doing superconducting research, superconducting Josephson junction related physics. And so talking about quantum coherence, people agree in atomic scale, coherence, of course, happens, but it's a big star, like a star. It's all quantum mechanics here, but quantum coherence it's not obvious. You cannot really superpose the two states of stars. It's impossible. Too much dissipation. But how about cat? People talked about Schrödinger's cat, but also that's too complex. This is a scale. Cat is about in the middle. And but can macroscopic objects exhibit quantum coherence? Yes, it is. This is what we do, superconducting qubit, which is very large. This is qubit, and you always couple it with superconducting resonator, which is very big. So it's almost like a millimeter, and millimeter you can also see. And this object behaves quantum coherence, and it's quite amazing, and involving like billions of conducting electrons. The states involving that much electrons, but they behave quantum coherence. So the problem is, how do you suppress decoherence? If you can control decoherence. You have to design this cleverly. You can do it. And so this is a brief history of physics and technology in superconducting electronics. And the first is Josephson. He got Nobel Prize soon after his announcement of Josephson effect. And then, quantum voltage standard, this is technology developed, and Josephson mixer detectors. And then SQUID, and of course, it's a magnetometer, it's a great sensor. And Josephson computer too. It was very fashionable that time in 70s, and it stopped at around 1980s, but 83. But still, we still have effort in this fast classical computer. And then it comes macroscopic quantum tunneling suggestion by Tony Leggett. Can macroscopic object like a superconducting system tunnels? And the answer is yes. And experimentally was demonstrated soon. And also it comes Kostya, Likarev, and Dima Abering about the single electron tunneling. So Josephson talked about the phase degree of freedom, and then they talk about the charge degree of freedom. And this is the only two degree of freedom in superconducting system. Every other degree of freedom is frozen. The only thing you can change is phase and charge. And then and soon single electron electronics was developed, and it is still being developed. And then there's a high TC things, high TC wiring, and then quantum coherence. This is our work done in 1999, mainly in NEC, and and then quantum computer is being developed soon, and this is the background. Let's forget about that. So what is Josephson junction? So this is the first talk about superconducting qubits. So I'll briefly introduce the physics, this is the heart in the heart of the superconducting qubit. So it's a junction. It's a two-piece of superconductor, weakly coupled here, and weakly means this can be a tunnel junction, can be other type of junction, but typically for superconducting qubit, you have to have a tunnel junction. This has to be insulator, and the macroscopic wave function of this superconductor here, its older parameter, it's called TSAI, and then there's it's just a complex wave, and it has a 2 degree of freedom n and phi, and so if you project that in 2D instead of 3D, like a real part, you see like a wave like states. And degree of freedom, in this case, if you forget about the amplitude, which is related to the number, if you just look at the phase, there's a phase difference degree of freedom that you can change the phase at the junction, because you have two waves, and then you can adjust the phase. And so this phase, it turned out to be the supercurrent flowing here. Supercurrent is some macroscopic current that you can measure with your ammeter. And this supercurrent is related to phase difference across the junction. And this is totally quantum mechanical property. And so quantum mechanical property that you can see in macroscopic system, and which is called macroscopic quantum states. That's why this is called macroscopic quantum phenomena. Okay, and from the Josephson relation, the states of Josephson junction. This is the toy model of Josephson junction. Two pieces of superconductor coupled here. It's given by some like a particle, in a potential, and potential this is cosine fine potential. This is called washboard potential, and this is a nonlinear system, and so classically, so this states it's oscillating here, some plasma oscillation, but it's something classical picture, and to be sure, the states here, it's involving all the electrons near the junction. So it's a huge number of the conducting electrons or Cooper pair is involved in these states. And but quantum mechanically, if you treat this in quantum mechanics, it will quantize. You have a quantized state. Just like, without this potential, you can change phase. Phase is not quantized. Like, electron in free space is not quantized. But once it's trapped in atom, you get quantization. And just like that, you have a quantized state here if you have this Josephson potential. And so once you have a quantized level, this is already qubit. And if you can control these states by applying microwave or something, inducing Rabi oscillation, you have qubit. So this is basically basic physics of qubit or Josephson qubit. And tunneling was discovered This is the suggestion, and then experiment came. Quantization of the level was discovered in 85, but the quantum coherence was not observed until, as I said, 1999. Okay, here, in 1999. That was 23 years ago. And so this is the first qubit. I showed you the pictures 20 years ago. And soon after our experiment, two other type of qubit, a phase qubit. This is just what I depict, single well potential qubit. This is called phase qubit, and then there's a flux qubit. I'll talk about this two kind of qubit later, a little bit more, but just give you the basic family tree of qubit. And D-Wave, it's a company in Canada, D-Wave system. Now they have, this is last year, they have 4,000 qubit system, annealer, quantum annealer, and now they are developing much bigger one already. And then this charge qubit was developed into a much bigger system over 23 years. This big companies are IBM, Google, Intel's are all working on this. Typically, they have about 50 to working on to or 100 qubit. That's the state of art these days. And also quantum supremacy, USTC China recently had using 66 charge qubit develop a very, very strong quantum supremacy experiment. So this Google and USTC are doing quantum supremacy. So it's developing very fast and strong. And so it's hard to compete with this big groups now with, if you are working in university. And then again, so this is, we're still talking about the qubit, superconducting qubit. As I said, qubit is something in between like a cat and atom. So this is the first generation charge qubit and flux qubit. It's 1 micron. But now, as I said, it's almost, this is already millimeter, close to millimeter. It's getting bigger and bigger. So a charge qubit, it's since if you have 1 Cooper pair tunnel into this island, there's a charge island. If you allow 1 Cooper pair to tunnel, you developed you have 2 different voltage states, and that involving many electrons, movement of many electrons. And these are macroscopic voltage, and you can superpose these 2 different voltage states, and this is called charge qubit superposition. You can work on that. Flux qubit is, you make a loop, superconducting loop with Josephson junction here. Then you can define permanent current in counterclockwise and clockwise rotating current, circulating current, and you can superpose that. And if you can superpose, this is called flux qubit. Typically, here you have 1 electrons, but now you have like 10 to the 8 or more electron, huge number of the electron involved in these states, and they behave quantum mechanically, amazingly. And then if you have like 10 to the 8 qubit, then you have, this is, it's called quantum computer. It's almost like a cat, big cat behaving quantum mechanically. This is my view
10
of
minutes more.
quantum computer. Excuse me?
10 minutes more.
Oh, 10 minutes more. Okay, I have to speed up. Thank you very much. So this is a flux qubit. Typically, you have a superconducting loop, and you have a hole. And here's the Josephson junction. And if you allow coherent tunneling of flux, quantized flux, then you have you can create clockwise current or counterclockwise current, and this is flux qubit, and charge qubit is just inverse of that. So now here's the donuts, but this now the hole in the donuts is filled. This is superconductor, and donut is gone. And then what? And there's a Josephson junction here, and Josephson junction here, you can tunnel, as I said, Cooper pair, one by one, and you can change the number of the Cooper pair on this island. And if you have two states, and that's a qubit. And so that's a basic picture of this two type of superconducting qubit. And this is the first charge superconducting qubit, and this is something oscillating in time. And so this is the result or demonstration of the coherent control of superconducting states. And this is example of flux qubit. This was done in Delft in 2003, and what is oscillating in time between 0 states and 1 states. So going, you have a clockwise current and counterclockwise current, and it's coherent oscillating. And so this is another demonstration many years ago. And okay, so we in previous talk we talked about many different type of qubit. So when you compare technology, you have to compare gate speed and error rate, because since this is an analog device, and you have to be very accurate, otherwise error will accumulate. So you have to have fast gate, and also a very error-less device. And here, these are the comparison with other technologies. Superconducting qubit is here. 1 bit and 2 bit accuracy is here. In accuracy, that trapped ion is the champion. They have a less accuracy, less error. They have 5.9. The superconducting qubit is working toward 4 nines. So roughly, this is the technology, and also we have to have integration. Integration is also very important, and superconducting qubit is very good at integration. Okay, so I'll skip this. There are many, universal quantum computer and optimization and quantum simulation, things like that, that you can develop. I'll skip this. This is the okay. Year and integration level, they're developing exponentially fast. Integration is getting more and more, and roughly tenfold in 4 years, and that's very good. This is like slightly closer to the Moore's law, but it's slightly different. We have to, the qubit, the chip has to becomes bigger and bigger, not like in Moore's law in a classical sense. Okay, okay, I can explain more, but I don't have time to go through. This is the progress in coherence time, and over 20 years, the coherence time increased maybe 10 times in 2 years, roughly, in these pictures. And now the coherence time can last for almost to the millisecond, and the longer it lives, you can control them more accurately, and this is good. So, okay, this is compared to the classical computer and quantum computer. It increased 2 to the n power, and so it crossed over in 2019 by Google, and at 53 qubits. This is the supremacy experiment. So this is a classical gate, and which is gate is arranged in space. So this is classical way to do. You have OR gate and AND gates. This is called the basic gates. And then you have a less number of the input and output, and you have a very complicated connection here. Instead, quantum computers, it's arranged. Okay, so I don't go very fast. So everything is done in space. It's almost like, so logic gate is arranged in time instead of space. So in each time you have to play like a playing piano. You have to play, you have to touch each qubit from outside. So the wiring, Franco talked about this wiring problem. This is because you have to wire each qubit from outside, which is very hard, not easy. And this is called the wiring problem in quantum computers. And this is a wiring problem. So you arranged qubit like this, and you have to, since you have to get access to the center one, you have to go up. You need something three-dimensional, and you cannot use insulator here because that will create decoherence. So something very complex system has to be created, and then we thought about the problem. This is what we did in recent years. We rearranged these qubit, and so you take all the qubit to the outside of the chips. Here, now this is rearranged, and now you have some local crossing internally. But you know, the advantage here is all the qubit is outside, so you can use the 2D control line instead of 3D lines, and this is much easier. This is conventional technology. So we are working on this. This is completely equivalent, and so for this, you can use air bridge technology, which is established to make some local crossing, and yeah. So it's. But however, you know, this big group like IBM and Google's others, they can make, in the beginning, I thought this is very hard, but they can do it in three-dimensional way. But anyway, 2D, at least it's easier, it seems. And we're working on this 2D. I can, this is showing how you you fold it like this, stretch and hold, and then the grid became this this bilinear array, and you can do the planar wiring. So this is the chip we made, 16-bit and 18 qubit, and all the qubit is facing outside, and I'll not talk about the details. And we try to see how much we can push. So we developed into 100 qubit system with this technology, and then its chip becomes very big, 20 millimeter, 20 by 20 millimeter. It's big. So we cannot really put this into fridge, but just to see how it goes. And these are the wiring, and then these are qubits, and Josephson junction. This is air bridge, and we have about lots of air bridges. So we can pack qubit, and qubit can be accessed from outside without any three-dimensional technology, and just regular wiring. And in the future, we can push it to like 900 qubit can be put into this size, which is not impossible. And maybe this is what I see in the future, according to our technology. Okay, so thank you very much. I think I made it in my time. And I'm happy to answer any questions if you have.
Thank you very much, Prof. So we have a few questions online. So let's take the questions online first, and then we'll take the questions from the audience. Okay. And so online, there's a question: can we create a Q-treat state? So not qubit, but Q-treat state in a Josephson junction. Can you see the question?
Yeah. Okay. So yes, we can do it. It's a nuisance. We do have many states. So in my cartoon, I just put 2 level, but we have upper states too. Yes. Okay. And the second question, what are the challenge facing the flux qubit? Challenges. Well, challenges, I guess, in flux qubit itself, it's not so hard to make. But you have to make a lot if you want to make into computers, and making a lot is always hard, and including wiring. Wiring is also tough, and also the accuracy.
Coherence. The decoherence is it?
Coherence.
Decoherence.
Yeah, decoherence. We can control let's see. So what's the typical coherence time of flux qubit? Let's see. It's not as long as the charge qubit. Charge qubit now can last for let's see, maybe half a millisecond, the best one. But flux qubit, there's a version called fluxonium. You use lots and lots of Josephson junction in qubit, and that I think it's comparable. It's 100 microsecond is possible using flux qubit, using fluxonium configuration. Okay, so
the main challenge.
yes, main challenge in flux qubit.
Yeah.
I think in main challenge. Yeah, of course, you want to make it longer. That's good challenge. You know, I said half a millisecond, you know, why not 10 milliseconds? That's big challenge. And also, like, there's a question here about the D wave. D wave, it's making 400 qubit, 4,000, and their coherence is really bad. They're using niobium technology, and they really didn't care about quantum coherence. You have to. There are many better way to do that, but you know, D-Wave choose some simple way to make it too. So, if you really want to make 4,000 very coherent qubit packed into a quantum annealing way, which that's a challenge, I would say. And then so what is this question? D-Wave is more powerful. Sure. Then yeah, well, not really. The D-Wave system, it's not the universal quantum computer. They can do optimization, and that's the only thing they can do. And so it's a specified. It's a you can. So that's the only thing. And then, as I said, their coherence property is not very good. And so the question is, under such a condition, can you do annealing very fast? And also, even if you have quantum coherence, it's not so clear that the quantum annealing it's not can be useful. It's quite for quantum computer. Mathematically, you can prove once you have a quantum computer, it's absolutely exponentially faster than any other classical computer in particular applications. But in terms of quantum annealing, the situation is not so clear. And so this is, I hope I can answer the question.
Yeah. I have a question here from.
Yeah, okay. So, and clarify again the distinction between flux qubit and charge qubit. Architecturally speaking, I'm not so sure. The physics-wise, the flux qubit, it's controlling the flux states. So if you have one extra flux, the condition of the circulating current changes, and so two states you control in flux qubit is states with different circulating current, so to say. And charge qubit, you're controlling two states with different number of the Cooper pair in the box. So this is the big difference.
Okay.
Okay.
We have one more questions from Oliver.
Thank you for the beautiful talk. It's really neat the way you're embedding the two-dimensional surface in a 1D line of qubits. I was wondering, since a lot of the new codes that are getting proposed require more than 2D connectivity with your Airbridge, do you think you could make a device that was more than just a planar surface, but had actual sort of 3D topology?
Yeah, I think this 2D thing has a limit, of course, and you have to, in the future, you have to combine some 3D connectivity. Otherwise, you can't. I mean, you hit the limit anyway soon. So yeah, we do have a limit.
I guess what I was trying to ask is you're putting qubits with an effective 2D lattice into a 1D chain.
Yeah.
If you wanted more than a 2D lattice, so if you wanted a 3D lattice, for example, could you end the same approach?
3D, you mean 3 array instead of 2 arrays? Is that? No.
Qubit with non-local connections in
No.
2D.
Yeah, well, I haven't really thought about this really tricky 3D connections. But the only thing I can, we thought about this, just making some 2D chip, and then you connect up this unit chip in using 3D technologies, and something can be achieved easily, I hope.
Thank you.
Yeah. So, okay, so I'll stop here.
Yeah.
I stopped sharing.